Chang.
I'm Kelsey, and this is our final lab project on absolute flatness.
So the purpose of this project is to measure the absolute flatness of the plano optical surfaces using the XPZ interferometer, and we also evaluate the accuracy using the reference flat. The Zygo XPZ interferometer is a laser fizzle phase shifting interferometer. The transmissive reference objective is translated for the phase shift. Comparing with the Newton interferometer, the air gap between surfaces is larger, and from this basic configuration of fizzle interferometer, we can see there is a collimating system and a Haney laser source. In this case, the interferometer will measure the flat wavefront so that the distance between the test lens and transmission flat will not affect the results.
Okay, so to set up this interferometer, start by aligning the axis for this reference flat. You have to cover it up so that you don't get any interference from the other flat. In align mode, turning the tip tilt to align the brightest dot in the crosshairs. Align the brightest dot for this one. Then we turn it to view mode to see the fringes. And then we continue turning the tip tilt knobs to get most fringes possible. And then we hit measure. We get a nice topographical map of the reference flat. It wiggles a little bit. So we close this to try to isolate it as much as possible from wind currents, but it's not a vacuum, so it doesn't work perfectly, and it still wiggles. To make sure that the camera is actually focused on the surface of the reference flat that we're using, we use this piece of paper with 2 holes in it and put it right up against the surface, change the focus, and get the picture as in focus as possible. Because this interferometer measures on such a small scale, it actually matters if there's dust on it. So we use this danger liquid isopropanol, we put a small dot, and then we gently swipe this across to clean it. There's this large peak over here. That's because there is a slight chip in the reference mirror. So what we do is we use the mask editor and we put this little circle to eliminate that. Say we don't want that part, measure it again, and boom, it's gone. And we get a much smaller RMS. The interferometer is oversaturated, so we change the light level up here and we go to just under oversaturation, so we get a nice picture. For the mirror, it actually has 2 sets of fringes. This is probably because the interferometer is measuring the wavefront from both the front glass surface of the mirror and the back shiny surface of the mirror.
From the Mecca lens, we see these stationary circular fringes no matter how we tip and tilt the mount, but we can still minimize the number of fringes inside of it.
As you can see, around the edges, it has a different fringe pattern than in the middle because there's a coating on the beam splitter that doesn't go all the way to the edge. So this is the data we collected from the interferometer. The power error represents the slope of the wavefronts. The peak to valley is the difference in height between the highest and lowest points on the surface. RMS is the average deviation of the surface. Theoretically, all of these measurements should be equal to 0 for absolute flatness.
We also collected the Zernike coefficients. They are used to express the wavefront data in polynomial form. These coefficients represent different wavefront aberrations, and we find the dominant aberrations. The most common aberrations are astigmatism and spherical aberrations.
We calculated the percent differences from the masked reference flat to each lens. As you can see, the percent differences are all very large, which proves that these flats are not really flat. The smallest lens came the closest. If 2 flats are actually flat, they kind of stick together a little bit and make it hard to pull apart because there's a vacuum in there, I think.